Thank you, Ria. Thanks for having me here. So what I'm going to mention is going to some extent to overlap with some of the previous presentations, but it's going to also bring new techniques, and it's very much aligned with what Jean-Louis Reisard mentioned as a first speaker. So I think by now everyone has understood the, let's say, the motivation for federated analytics. So the fact that this is a way to collect much larger amounts of data and to come up with more, let's say, with consolidated statistical results. So this is here is on this slide is one example, which is a study of the side effects of COVID vaccines, as we know, are very rare, and as a consequence, to be collected require actually having access to larger data sets where these kind of events may happen. So now the topic itself of, let's say, federated analytics done in an appropriate way, in a responsible way, or also called decentralized PPML solution, privacy-preserving machine learning solutions, has drawn already the attention of a number of researchers. And so I'm going to very quickly mention some of the approaches. One is the vanilla, what Jean-Louis Reisard was mentioned as the vanilla federated learning. Another one is multi-party computation, another family. That is this one. I'm going to come back to this. Is essentially the idea is to be able to carry out computations on data sets that are decentralized. The third one is a differential privacy, so bringing deliberately some noise in order to diminish the risk of, for example, re-identification. And the last one is homomorphic encryption, which means the ability to perform computations on data that without, let's say, on encrypted data, without seeing the data in plain text. Right? So I'm also going to provide the references to all these papers on the let's see, data set, the slide set that I'm going to deliver. So let me start with the one solution that we have developed for this purpose, spindle scalable privacy preserving distributed learning. The idea here is to, let's say, we've built essentially a system that is organized in the following way. So at the bottom, there is a technique that Jean-Louis already mentioned, namely multi-party homomorphic encryption. I'm going to come back to this in a minute. And another related technique is a cooperative gradient descent. Gradient descent, as you know, is something that is used quite extensively in machine learning algorithms. On top of this is the so-called extended MapReduce abstraction. So essentially, taking MapReduce and then extending it to the framework that we are considering here. And then comes the generic secure federated learning with data confidentiality and model confidentiality, which we want to protect both the data and the model. And on this, we are able to perform operations such as that fall under the umbrella of generalized linear models, so linear and logistic regressions, but also multinomial regressions. So for this, we need several building blocks. One is homomorphic encryption. So in a nutshell, the idea here is to be able to take Alice and Bob, so two stakeholders. One here, so Alice on the left takes her own data. She encrypts this data, sends them to Bob. Bob receives only the encrypted version of this data, and then performs a function, a computation that is on the encrypted version of the data that comes from Alice, and on his own data in clear text, sends something back. And at the end, so Alice will see the outcome that without having seen the at any point in time the input from Bob. And one can do this symmetrically, so which means that each of them can, let's say, essentially make computations on the other's data without seeing them. There's one building block. Another building block is secure multi-party computation. So as I mentioned before, so this is assume there are a set of players who are typically data providers. Each of them is coming up with its own inputs. Each of them is entitled to obtain an output that is computed out of these inputs. And so the idea, the goal is to make these computations while providing two properties. One is privacy. No party should learn anything more than its prescribed output. And the other one being, of course, correctness. And so they run this protocol. I spare you the details because that would take, of course, too much time to go let's say, in the mathematical idiosyncrasies behind this. But at the end of the unfolding of the protocol, each of them receives the output it is entitled to. And then the trick, the crucial trick, is actually to combine the two things, is to combine secure multi-party computation with homomorphic encryption. And this leads to a very powerful tool called multi-party homomorphic encryption, on which it is possible to build a number of solutions that are, let's say, support federated learnings while being privacy preserving. So, and so to illustrate how this works, so if you see here a simple example, on the left-hand side, you see here, let's say, it's a really toy example. Assume here's these 6 points, and the goal is to find the best possible interpolation of the line that interpolates those things. But you can, so would be, let's say, linear regression, but you can extend this also to logistic regression. And so if all data is available in clear text in a single place, then this can be carried out by a gradient descent. That's really a well-known technique. But to make the problem, the problem is more difficult if actually the data is distributed. And we will assume that one data provider has two of the points, so the first 2 points. The second one has points 3 and 4, and the last one has points 5 and 6. Right, so which would mean something of this kind, right? In this case, the perception of the world that each of the data providers has is quite different, right? And the risk as a consequence is that each of them, if they run their own data, their own gradient descent, they are going to end up in a different local minimum, right? And so the goal of Spindle and tools in that family is to be able to reconstruct the richness of making use of all the data, but without having to centralize the data. And so this is achieved in the following way. So there are, if you wish, each of the data providers, or each of the players, performs local iterations to compute the gradients, and then there's a global model that gets updated and refined little by little, and that will lead to the final model, but that is highly protected because at no point in time are the data centralized to achieve this goal, right? And so we have developed this system. It is now running, and we have, let's say, run several benchmarks on it. And you see here the result. So blue is what we obtained is the reference, essentially the accuracy for a given data set with the centralized data, all available in clear text. The red is actually independent. So if you just make independent computations on separate data sets, and then of course the result is of a lower quality, then yellow is distributed without protection, and green is distributed with protection, which is a Spindle. As you can see, we lose on the different examples, we lose relatively little, if any, accuracy when moving from blue to green. Then in terms of performance, what we show here is that actually the runtime to make these computations is in the order of tens or hundreds of seconds. So it's absolutely acceptable in most applications to have to wait for this amount of time. And there are still additional, let's say, improvements and optimization that are going to improve the situation further. So conclusions, here we have seen a generic framework to perform a cooperative gradient descent. This provides model and data confidentiality over the entire machine learning workflow. We have seen the scalability, and what we are going to see next is the application of this technique to genome-wide association studies and also to actually survival curves. And then we will see how to securely train more complex ML models that goes, let's say, beyond generalized linear models. So let me start with the application. So we like to call it the holy grail for secure federated analytics of health data, something called, this we have called Pharma. So Pharma stands for Federated Analytics based on multi-party homomorphic encryption. It's a joint paper with colleagues at the Broad and at the MIT. and that is about to appear in actually Nature Communications. So the idea here is to train and run ML models on decentralized data sets without seeing the data, as mentioned before, right? So here, what we have done is that we have taken an existing study of, in this case, survival curves with, let's say, a Kaplan-Meier computation technique. And what we see here on the left-hand side is the original, let's say, curves as they appear in the paper that was published actually in 2019 in Nature Genetics. What we show is that on the right-hand side is that we are able to reproduce the same results, in spite of the fact that what we do here is that we chunk the data set in 3 parts, encrypted, and as if the data, if you wish, were separate. And we show that we can reproduce the same results, which means that this brings a demonstration that actually it is absolutely feasible to operate on data sets that are decentralized, encrypted, without having to actually regroup the data in a single place. This is for survival curves. We have done the same thing for GWAS, for genome-wide association studies. And you see here the comparison between what was obtained in the original paper that appeared in PNAS in 2015, and the way we do this again by having split the data in several with several data providers. So actually the 2 results are really extremely similar to each other. So here again, it's about the performance. Though of course it takes longer because it involves a relatively advanced cryptography, but the execution time is in the order of let's say hundreds or a bit more seconds. Now, this is about generalized linear models. It is also convenient in some cases to make a more sophisticated computation. So instead of having GLMs that can be summarized by this or modeled by this kind of degenerated neural network, to actually be able to address fully, let's say, full-fledged neural networks. And this is what we've done in a work called Poseidon that we published at NDSS, which is a security conference earlier this year. For the sake of time, in order to keep some time for the questions, I will go relatively quickly on this one. So essentially the idea is that there is a querier. The querier generates the request to the community of data providers. The question goes around and is processed in a fully decentralized way and goes back to the querier with the response. How this is done is the same principle as what we have seen before. There's a local model that is trained locally at each of the data providers, and then there's a global model that is elaborated progressively in order to provide really leverage on all the richness of the various data sets that are available with the data providers. So this provides data confidentiality and model confidentiality, also in the way that we've seen before. Okay, this is essentially the principle. There's a first, if you wish, an offline phase with a key, cryptographic key generation and the model initialization, and then there is let's say the constitution of the local model as mentioned, and then the construction of the global model. Voila, and then the global model can be either kept secret for oblivious prediction or revealed to the querier depending on the policy of the system. And here again, we run this through benchmarks. So we see here we have a bit of loss of accuracy, but actually what we've discovered is that if we run the model for more time, then we can have the accuracy get closer and closer to the original accuracy. So it's not, let's say, the source of concern, is if provided that people are not too much in a hurry to have the result. Voila, and so this is again the evaluations in terms of performance, which are again in the kind of ballpark that I've mentioned previously. Okay, and then one more thing is let's keep an eye on what is happening in the quantum community. As you know, the quantum threat is maybe around the corner, who knows, right? As soon as quantum computers are going to become operational, some of them might be able to break all the existing public key cryptography. So the good news is that all the techniques that on which we are with which we are working are based on lattice-based crypto and are therefore quantum resistant. And we have developed a specific, let's say, a library called Latigo that is actually open source that achieves this goal. Voila. Now the traction around these techniques have become so strong that several youngsters in my lab have pushed for the creation of startup company. The startup company is called Tune Insight. Of course, I'm providing my help and my blessing to this endeavor, and we are going to incorporate it actually tomorrow, so on August 24th, 2021, because of the, let's say, number of people who have expressed interest in this technology, both within the medical field, but also outside of the medical field, is such that we believe that this is actually commercially viable. So the name is Tune Insight. With this, let me conclude. So as you have seen, parallel distributed machine learning is actually feasible. The solution we recommend is to leverage on multi-party homomorphic encryption. In this way, it is possible to perform computations without seeing the data. It is counterintuitive, but the properties are mathematically well known and proved. These are techniques that have been around in computer science for decades. This relies on decentralized trust, and there is no need to transfer the data. That's a big plus, right? And this technique protects the partial aggregates. So when we've seen the willingness of a company such as Sophia Genetics to share data across different jurisdictions, so this is typically a solution that can be used for this purpose. So now we've seen also the scalability with the number of data providers and the size of the data sets. And we believe that this will really be a game changer for machine learning in pharma and more generally in health data. And we've talked also about Tune Insight. I'm providing also here a URL, dpph.ch. This stands for Data Protection for Open Source Health, a project in which we are involved here, a nationwide project in Switzerland. And let me mention also on the next slides, the references on which this talk is based. As you can see, there are quite a number of researchers, of course, also beyond EPFL, who are working on these topics. And I thank you for your attention.
Thank you very much, Jean-Pierre. I have a question. A previous speaker mentioned that she would like to see more metrics for the levels of the identification of data. Is that feasible, based on your opinion? What would be the challenges to implement this type of identification?
So, as mentioned, in the system that we are proposing, what happens is that we, and this is something that Jean-Louis also mentioned, the key, the cryptographic key for the decryption does not exist at any point in time as such, right? So it is actually a collective work that makes it possible to decrypt. And this means that in order to break the system, an adversary would have to compromise or to bribe or to intrude in all the systems that are involved in the Federation, which seems to be de facto infeasible. And as a consequence, we consider that it is reasonable to consider this that the data that are processed, so to say, the partial aggregates that come out of the different data providers can be considered not just pseudonymized, but really anonymized data.